Okay. And I need, all right, so we're recording. So, all right. So let's think about this one, okay? So remember, what we're trying to talk about right now is, how do we get these derivatives, right? How do they fit into the code? So I need to write out a function. So remember, as I said, we have the two functions, y and j, right? And you visualize that you have something like this when the EC function is quadratic. And this then is x2. Do you agree? Yes? All right, good. So that's the function that gives you this, right? But what we need is the function that tells you the slope, right? Either like this, like that, or like this. So then we take the derivative of this function to get that. That's just how it works. So what's the derivative of x squared? 2x. Just like that. It's just a rule of calculus. And so this is literally what we need to do. And then once we have that, we have what are called the gradients, and we can update the weights. So this process is generally done by TensorFlow or PyTorch or all of them. They do it for you because they're doing it for every weight. If you have 52 billion parameters, that's a lot of derivatives, right? And so it gets pretty complex and it has to be done very efficiently. However, just for intuition, we're kind of exploring this idea manually. All right, so then that means let's start with an example here. So let's assume, so let's just say assume j of the form, so I'm going to say f like this equal x3 minus 3x2 plus 7. Do you see that? That's the original function, the j. But as we are processing things to calculate the gradients, we know that, we need to know when we update minus LR, right? We need to know if it's a plus, a minus, or a 0. So the theory basically says you take the derivative of it. Okay, so now we assume this function. We need to optimize, obviously the parameter that we need to optimize here is for x, right, for this example. So we will need a value of the derivative. So what I'm going to do is the derivative of this one will be f, usually denoted like that. And the derivative of this is, who can tell me? It was already in the code, right? So 3x2, right, minus 6x. Okay, so that's the derivative. How do you know this? There's a book of rules that, given these, it's a set of rules basically that allow you to take one function and derive it. Okay, so this is kind of like numerically done by the solvers in TensorFlow and PyTorch. They just know how to do it and compute it effectively. But the beauty of this is once you've done this, you plug in the values and now you get it's not letting me write. Now you get the answer then. You see that? Okay. So we're going to just do a little example of this. And then after that, so now we can, then after that, we can move on. So I'm going to switch to the Jupyter Notebook. Right. And you can see this is why I threw in there 3x or 3, what is it? Yeah. So the function was x3 minus 3x2 plus 7. The derivative of it is 3x2 minus 6x. All right, so now that's this function over here. Got it? So we have the original one, but we also have the derivative of it just so that we can see it, although we would not have to compute this manually. All right, so now, given that information, we need to set up some parameters. So we're going to have, we're going to need step size, which is the learning rate. So that can be 0.01. We also, yeah, let's just leave that there. So now here we have a new x equals old x minus step size times, and then now we do function derivative. Function derivative where we plug in some value that we had for the weights, right? Something like old x, for instance, whatever it was. Okay, and so this is kind of the idea of what is happening, right? So before we had the updates of the weights, but now we can compute the value that goes in here by just having the derivative of it. Does this make sense? Okay, so what we will do as we start playing with some of the multi-layer perceptrons, logistic regressions, is we're going to hard code this into the program. As it turns out, the functions will never be as complicated as this one, right? Or change as much. So this was just an example to illustrate the derivative itself, right? But really, we're always going to be using a specific type of loss function, right? And so it's always going to be the same type of equation, okay? So we kind of know in advance sort of what it's going to look like. But this is the idea. So you have, imagine the original J, take the derivative of it. And so when you do in the code here, you would use that, right? And you plug in your values to do the update, okay? So that's the basic idea. Any questions on this? Make sense? All right, so I'm not, you wouldn't do this, right? So you wouldn't do it precisely like this. This is where TensorFlow just does it for you. In fact, if you remember, there's only those two, the optimizer that we define and also the loss function that we define, right? So all of that is, but this is really what's going on. Okay. All right, so now let's talk then. Now we're going to start getting into Keras itself. So this was just some intuition from scratch. Now we're going to get into Keras itself and try to relate this or relate Keras back to these ideas. So let's go back to the whiteboard. Okay. So let's actually call this Keras and losses. Okay. So as it turns out, it's a great thing about deep learning is that there aren't that many losses that we need to choose from. So it's not like there's 30 or 200, right? Or so many equations. In fact, for the most part, like in my experience, I've used 4. That's it, right? And I literally always just put the name. I never go as far as hard coding the equations. You can, but it's actually not recommended that you type up the equations, because what can happen is you can end up with underflow or overflow problems. You know what I mean by that? Like division by 0, not a number, and so it's, whereas if you use the built-in functions, then Keras handles a lot of those errors for you. But let's go over this idea. So now I'm switching to Keras, right? And I'm calling this losses, okay? So again, I'll take it slow here, just kind of read through some things. So Keras provides many built-in loss functions to choose from. Or you can create your own, as I said, you can. And if you were doing research, right, then maybe you can start playing with losses, but it's very rare that we get a new loss function, right? Those they're pretty solid. However, as I said, I've used 4, and here the notes say three of the most commonly used are, so 3 of the most commonly used are MSE, mean squared error, okay? Categorical cross entropy, categorical cross entropy, okay? And binary cross entropy. So what is their difference, basically? So MSE you use when basically regression. That's how you should remember it. And what is regression? You're predicting real valued numbers, right? So you're predicting not a class, like is it a 0 or a 1, but you're predicting what is the price of that house. So like 275,365, right? That's a regression. For classification, notice you got these cross entropy. And why do we have two? Because the binary one is when you only have two classes, either like 0 or a 1. And the categorical cross entropy is when you have multi-class. Okay, so that's going to be 0, 1, 2, 3. They're just, it's the way they work. Make sense? And believe it or not, that's it. There's another one called RMS prop, but in general, these are the ones that you end up using, even if you're doing very advanced deep learning. So the three most commonly used are mean squared error, categorical cross entropy, binary cross entropy. It is very important to understand when it is appropriate to use each. And I just kind of gave you that information. Okay. If your neural network is designed to solve a regression problem, then you can use mean squared error or MSE. So this is mean squared error. Right, and I'll just denote the equations here. I've written this equation many times, but just since I'm going to give you the cross entropy equation, now I will give you that equation. I want to do it in relation to MSE. All right, so I'm going to lay out MSE first. Formally now is basically an average K of errors. So you take, 1 by n is the number of samples that you have in the train set or the batch, and then you take the mean of it from I equal 1 all the way to n. And this is going to be y hat to y. That's kind of how I usually write this down, right? And square to get rid of the error. There's another one which instead of using squared uses absolute value. So that also works, okay? But usually this is the approach. Any questions on this one? That's the equation, right? And it should be familiar to you. Again, please remember, very important, there's a way of understanding this visually, which is the bowl shape or a convex function, which is guaranteed one global minimum, okay? All right, great. Now let's move on to the hard stuff, but also very interesting. When you have a classification problem, this is when you're learning classes, right? You're predicting, it's a cat or a dog. Then you use cross entropy. Cross entropy is a topic from information theory, right? So Claude Shannon again, right? Even in AI. So Claude Shannon, when he was working on all this, he defined those principles of information theory, and all of this comes from that. So if you're working on a classification problem where each observation only belongs to one class, so that's going to be belongs to multiple classes. Let me say that. We're going to call it categorical cross entropy, also multi-class cross entropy, which is probably more intuitive. So the equation for that, so that's going to be, I'm going to use multi-class cross entropy, right? The reason why we have to say multi-class cross entropy and binary cross entropy is because it's two equations. They're similar, but they're definitely two different ones. And they're written that way, and they have different names in Keras. Okay, so you have to call either binary cross entropy or multi-class or categorical cross entropy. So the equation for this one looks like this. I'm going to use the J again, right, to designate the equation, and it's going to be from I equal 1 to n is the sum, right? So remember, this just means the sum, and we have yi log of y hat. You see that? That's it. Although it sounds scary or looks scary, that's basically the function. All right, so now important things, basically two things that are important here. Notice that you have the real and the predicted. So that's how in relation to the previous one, you have the real and the predicted. You guys see that? Does this make sense? Okay, you have the real and the predicted, right? In the MSC, in the cross entropy, you also have the real and the predicted, but in a different way. And you have this log symbol. Okay. Now you can ask yourself, how did they come up with this log, and how did Claude Shannon invent all this stuff? But really, what's important is there's an easier way to understand this, and it's by this, right? The intuition of the visualization. So in the visualization of cross entropy, you guys remember that we have the W's and the J's, and the relationship that governs this, or the thing that governs this relationship, is this equation that looks like this, right? So we must have an equivalent for this one. You see that? And we do. And so we're going to see that we have still something like this, but these now have various representations, and they have the following shape. You see that? So we're going to study this for the binary case, which is the one that's most easiest to understand, okay? But cross entropy basically governs the relationship between W's and J's in this way, okay? So if you notice, it's no longer this concave curve like that, but now this function, the logs, look like this. It's a curve going down or a curve going up. Everyone with me so far? All right. All right, so now, so that's important, right? Because that helps you to understand, why was this equation the way it is? It's because it has this relationship, and this relationship is actually quite intuitive. Okay, so let's look at the case. Now let's dig really deep and look at the binary cross entropy, which might be a little bit easier to understand. So binary cross entropy. So in this case, we only have two classes, right? So that's the important thing. Two options, or two classes, something like 0 or 1, right? That's what we've explored that problem quite a bit. So how does this equation look like? So this equation looks like the following. Sometimes you have these averages, you can pretty much disregard those in terms of like the intuition of it, but it's not so important. So here we have, it's still a sum and an average, right? Basically, you're taking an average here, right? Because it's the sum divided by n, all right? From I equal 1 to n. Now, this is what's going to be pretty important. If you remember, for the multi-class, it looks like this, right? And we still need this log to be able to create these shapes, okay? But now we're going to do this. So first I'll write the equation, and then I will draw the graphs. So this is, just to be consistent, I'll say yi log of y hat I. This is a log, sorry. So great. All right, and then we have plus 1 minus yi log 1 minus y hat, like that. And there's an I. That's the equation of binary cross entropy. So yes, this is denoted by J. Do you see that? But these are the three. There's one more, the RMS prop. We're not going to cover that one. What's important is, again, to understand the intuition, as I was saying, right? So remember, what are we doing? This is the inference function. We compare it to the real, take the difference. It's called MSC. That's for regression. What's important is this equation basically creates this relationship between the W's and the J that follows this. Guaranteed concave, guaranteed global minimum. Multi-class just looks like this, cross entropy. So that's same problem of classification, but we have multiple classes. Simpler, and it has this shape that looks like that. Binary cross entropy is actually the same thing, right? It's just we write it in this way for it to be convenient. So that's the equation. All right, so now let's look at the interpretation. So there is the equivalent visualization of it. Do you guys see that? And so there's the J side. The J is usually the cost. So our goal is to minimize. And we do things in terms of W, which are the values that plug in into the inference function. The inference function is this one, right? And that allows us to predict, and we compare it to the Y. Do you guys see this? Now, we only have two options here, right? What are they? Those are determined by the real values, because it's binary cross entropy. What are the options? 0 and 1. 0 and 1. So how do we denote these? We're going to say that the real class is 0. Or over here, the real class is 1, equal to 1. So what does that mean? It means, think about it. If the real class is 1, you want the model to predict the 1, correct? That's what you want. Yeah? Does that intuition make sense? And if the real class is 0, you want the model to predict a 0, right? So you want to minimize when it's 0. Okay, so the way that you can think about it is that you have that, or you have that. You see what I'm saying? So if it's, so did I write these? I wrote these actually backwards, sorry. It's the other way around. So if it's 1, oh, no, actually, yeah, like this. And if it's 0, yeah, like this. Is that how I had them? Or did I have them backwards? I don't know. But this is how they should be. Okay, so what this implies is this is 0, this is 1, this is 0, this is 1. So when the class is 1, right, over here, right, we minimize the function like this, right? So as we start going down, we minimize. And then on this other side, if we want it to be 0, we get this behavior here. Do you guys see that? Yeah. All right. So another way of thinking about it is, if we plug in here, let's say that the real class is 0, then for this one, the class is 1, right? So this component basically goes away. So when the real class is 0, we get rid of a whole section of this model. So you guys see that? And then when the class is 1, so if the class is 1, which one do we keep? 1 minus 1, so this goes away, right? So we are only left with this one. So basically what that means is this part is this, and this part is this. Does this intuition make sense, guys? So we create a loss function for binary cross entropy that looks like this. And it works magically in the sense that whenever we want the real value to be a 1, right? It plugs the 1 here, and it plugs the 1 here. So 1 minus 1 is 0. The whole thing goes away. Only this section stays, and this section looks like this. So that means that this function can be represented by this graph. And so basically we minimize, right, the cost like this. And let's say we have another sample. So the other sample is 0, right? So if it's 0, 0 here cancels this whole thing. This becomes a 0. 1 minus 0 is 1. So this whole section remains, and this whole section remains. that remains creates a graph that looks like this. You see that? And so because this governs the relationship, that means that we minimize in this, which basically means we minimize when the value is 0. That's binary cross entropy. So it's similar to the MSE, right? Which had a relationship like this, but this one has this relationship. And that's it. I mean, that's basically the idea. Okay, so that's how we are able to minimize the values that we have. So whenever, in conclusion, I should say, whenever you plug in a loss function, right? Let's say you want to do a classification, you want it to be binary, so you select binary cross entropy. Even though you only write the name, what is happening behind the scenes is you have this equation. Could you in TensorFlow write this equation? Sure. But it's not even recommended to do that. Instead, you should just use this. But at the end of the day, then, whenever you get a real sample, the inference function should give you minimize basically based on this relationship. If it's a 1, it's minimized here. If it's a 0, it's minimized here. And that's it. Any questions on that? Clear? All right. All right, well. All right, so like I said, if you have any questions, then definitely let me know. But that is the idea. So let's go through this. Yeah, so where is this coming from? Okay, so we have a few minutes, so let's go over here. So all of this is coming from the section in Keras. So what I can do is go to, yeah, I have this. All right, so let me share the GitHub. All right, so we're going to go to one of the code examples in the Machine Learning Foundations section. We did this. So Keras and Cypher 10, right? So that's the latest that we have. And all of this that I've been talking about falls into, where is it? Here. This. Okay? Everything that I've been talking about. So the categorical cross entropy, we're using that type of cross entropy because we're doing 10 classes, right? But if it was a binary, we would use binary cross entropy. But now you know that behind the scenes, we have that equation. And those equations, basically, all they do is they govern the relationship between the weights and the minimization of the loss. There's only one way that they can minimize the loss is through that curve that is defined by the fact that it's cross entropy. Okay, and it has that relationship. Okay, so we saw that. And then we have the other thing I did at the very beginning, which is doing the update, and that just uses the atom optimizer, taking the learning rate. So these 2 lines of code are basically handling all of this, right? And then we just have the theory that we have discussed. Go ahead, please. So if you did this in CUDA, which is the C++ NVIDIA library, you did have to code a lot of this. But even then, you did have solvers. Like, you didn't have to code everything. Like, there's something called the chain rule and everything. You would use solvers for it, basically. What's it called? MATLAB also was what people used 15 years ago or so. And that it still exists, and it has a lot of solvers, but you just had to do more of it manually. Nowadays, thanks to TensorFlow and PyTorch, all of this is done in just these 2 lines of code. So it's it's very helpful for sure. Keep in mind, TensorFlow was only released at the end of 2015, I think. So before that, there was none of this. 7 years. Yeah. All right. Yeah. So all of this is usually done in C++ also, right? Remember that Python is really just an interface to all the compiled code in C++. So that's why it's really fast. All right. So the optimizer is the algorithm that will be used. So I'll just kind of summarize everything that I've said. as you guys are looking at this code, right? So the optimizer is Atom in this case. Also, with regards to optimizers, there are only two: stochastic gradient descent, SGD, or Atom. And Atom, just like with everything, almost like the same idea as the CNN, right? CNN had the batch normalization, dropout, residuals, improvements, right? That's what Atom is. Okay, it's like they haven't reinvented stochastic gradient descent. They've just improved it. So in general, I like to use Atom. A lot of people just use Atom nowadays because it's improved. But I'll just summarize. So the optimizer, which is this one, where you only have to provide the learning rate, is the algorithm that will be used to update the weights in the neural network. Okay, so I think I still have that code. Yeah. All right, just like this. Okay, so what's happening is it takes the function, calculates the derivative, then that derivative basically literally plugs in. Okay, and then you have and this, remember, you update the weight. So in fact, we went from perceptron, which you know all of that, but perceptron did not have this part here, if you remember, right? This is the part that's happening. And this function is actually the J function, so the cross entropy, right? But the cross entropy with the neural network architecture inside of it. Remember that. And so you take the derivative and now you update, okay? Because it gives you this idea of the tangent, okay? Remember that the neural network goes in the loss function, because let me see if I can switch back to the whiteboard. What I mean by that is this. And I'll probably do this in MSE, which is a little bit easier to visualize. So in MSE, what is y real? It's just a value, right? But what is y hat? Who can tell me? What is y hat? Okay, and where does that come from? The inference function, right? And the inference function, remember, for a line, it is something like x w plus b, right? But really, this is not a line. This is a deep neural network, right? So remember that this is actually y hat, right? But over here we have x, w, and these are vectors also, plus b. And these, by the way, go through functions. And these, by the way, create layers. And this, by the way, layer h1, right, plus b becomes what? h2, correct? You guys remember this? Right, so remember, a deep neural network looks like this one, okay? And then this h2, w, and remember, this is 1 and this is 2. So there are different weights, right? They're not the same set of weights, okay? So to be yeah, it's W2 because it actually corresponds to this H2, not to the previous one. So this would be, let's say 3, just for sake of argument, plus B. So this y hat is this y hat. Is this clear enough or no? So the J is this, but this goes in there. When you take the derivative, you take the derivative of the whole thing. You guys see that? Any questions about this idea? This is what makes it non-convex, because it has multiple solutions. So it is the fact that you have the neural networks, okay? Please remember this idea. We're going to come back to it. But the thing that makes it not bowl-shaped is this fact, that you add multiple layers, and multiple layers create symmetry. So you can solve this problem by shifting the weights to one side of the network or symmetrically to the other side. What does that mean? You have two solutions there, possibly. Do you see that? And so it starts to create multiple options. And that's what makes non-convex problems, okay? So that's really, we'll come back to this idea, but I'll just throw it at you for now. All right, so the optimizer then, to summarize, is the algorithm that will be used to update the weights in the neural network based on the gradient of the loss function. All of that is kind of what I just said. This is how the speak of machine learning. So the gradient means the derivatives of the loss function. So the optimizer atom is the algorithm with stochastic gradient descent, the update rule in the loop, that will be used to update the weights in the neural network based on the gradient, the derivatives of the loss function J. In this case, cross entropy, but cross entropy that integrates the neural network inside of it. Okay, because everything is linked. So this is what TensorFlow does. TensorFlow is actually a computational graph that literally links all these tensors and creates the flow of it. It's literally, that's why it's called TensorFlow, right? It's how the data flows through. So if you notice, you define these weights and biases. This is your network. These are the things to learn, and the data is flowing, right? So it, you know, it flows, and then it flows, and it flows, and then it flows in here and compares to the real, and you know, that's how it works. Okay. All right. So hopefully that made sense. So one of the most commonly used and stable optimizers is Atom, as I said. In most cases, you shouldn't need to tweak the default parameters of the Atom optimizer. Okay. Except for the learning rate. Remember, that's something that you do tweak. So we talked about that. Yeah. And that's kind of that idea. All right. So now we have a few minutes, I guess. Let me see. Yeah, sorry about the video thing. That's, yeah, so this is, I may touch on this topic again on Monday. Okay, I'll review my notes just to make sure I didn't miss anything. So I may come back to it as a kind of a review, and then we're gonna pick up, yeah, basically I think it's 7:38, so we can, but we're gonna pick up on the next thing I was gonna cover today is this. So I added another script here under NN maths. So you can start looking at this one. It's called computing the gradient. So just like I showed you about the derivative by hand, and I showed you the derivative in that hard-coded version, now the next step was to take a look at it, but through TensorFlow. So actually TensorFlow would do this for us. Okay, so you can take a look. Same idea. We have a function. This time we have this function, which is the loss function. Think of it as cross entropy. We have some values, right? We have, then we plot it just kind of like before. And then here, if you notice, we use TensorFlow to calculate the gradients, which is basically taking the derivatives. So this will prove to yourself, for instance, as a kind of a informal homework that I won't grade. Take this function, okay? Where's the values? I think I have two values. Oh, here, no. Shouldn't have. Oh, here, these are the values, 3 and 5. So W1 is 5, W2 is 3, okay? So write that down. So now, take this function as the original function, which is 3 times W1 to the square power times 3 plus 2 to the W1 times W2. Okay, that's the equation. That's the original one. Take the derivative of that, which is going to be the partial derivative in terms of W1s and W2s. And then once you have that, you're going to plug in the values 5 and 3, and you should get 36 and 10. Do you see that? So basically, if you solve it by hand, it's called the analytical solution, right? So you can work that out. We'll do it on Monday, but just as fun, you know, calculate the analytical solution, and then we're going to prove that the gradients mechanism in TensorFlow also does the exact same thing. Right, and that kind of will show us that, you know, this is how it works, and, you know, but anyway, that's the idea. Okay, so we'll continue this. Yeah, so it's 7:40. We can stop here for today, and then I'll summarize a little bit on Tuesday, and then pick up on this one. As I said, the next couple of lectures are very theoretical, but we'll be done with that soon, and hopefully you'll have a good understanding of what's happening behind the scenes. Also, I remind you for Thursday, please don't forget the competition, right? So homework part B, the competition is Thursday, and I will bring the trophy and announce a winner, right? Whoever gets the highest score. So I can't, competitions have a limit of time. So yeah, please.
So what do you?
Yeah, a report, a PDF report, yeah, of how you did it, what the highest score you got, what your architecture was, that kind of thing. And then, yeah, and like I said, I think it's a competition, right? So win, do whatever it takes. Except no ringers and no loading to websites that solve it for you. Okay. All right, have fun with it. That's it. Have a good weekend.
You do.